What's up, guys? Yeah, so we're going to go over the worksheet for week 1, just basics of velocity, acceleration, and we're going to go and use those 5 equations that we learned throughout this past week, and we're going to talk about like free fall and all that good stuff, right? Those constant acceleration equations and then free fall. Yeah, if you guys have any questions about anything as I'm going through it, I know this isn't as interactive as it has been in the past, but time's weird. But yeah, if you have questions, go ahead and comment on the video, and I'll be going through the video comments throughout the week, and I'll try to answer as much of them as I can. Or if I do something that you think is wrong, go ahead and comment on there, and I'll check it. And I'm not infallible, so might make mistakes here and there. That's all good. Okay, so number 1, right? Also, I've never used like an iPad before, so here we go. Number 1, these graphs aren't perfect. I know B and C are kind of weird, but A should be pretty straightforward. So for 1, I just gave you the position graph, and I wanted you to estimate what the velocity and the acceleration graph would look like. Okay, so let's look at the position graph. So the position graph, it just looks like a linear diagonal line that is pointed in the positive direction, right? So we can imagine our car is starting from some origin, and it is, as it starts and as it goes, it is going at the same rate all the way through, right? Wherever it's going at the same rate, right? So I know it's going at the same rate because the change in distance is the same throughout, right? So you can also measure that by the slope, right? The slope does not change throughout the graph, right? It's a constant linear slope, which tells us a lot about the velocity, right? Because the velocity, we find the velocity by finding those, this slope of the position, right? So we see that we have a positive slope, our position graph, so it's going to tell us that we have a positive velocity, okay? And we have, like I said before, the rate isn't changing, right? The rate of change of position is not changing. So that's going to tell us we have a constant velocity. So that's going to give us a velocity. Let's say our slope here is like 2 meters per second, right? So then our velocity graph is just going to have just like a straight line at, let's say this is 2, right? This is like 1. We're going to have a straight line just like that, right? So we have a constant velocity. Our velocity is not changing throughout. It's a positive velocity, right? Because our line is pointed upwards, right? Our car is moving in the positive direction on the graph. And yeah, so again, our velocity is just the slope of our position, okay? And the same with acceleration, right? The acceleration is just whatever the slope or the rate of change of velocity. So do we see a rate, any change in velocity? No, we don't see a change in velocity here. It's a constant velocity. So if we look at acceleration to be the rate of change of velocity, there is no change in the rate. So we're going to have an acceleration of 0, right? So our line's just going to be like straight down here. All right, cool. So that's A. So part B. Okay, so for part B, what do we see? Well, we see that our car, again, is going in the positive direction. Okay, it's going upwards. But this is more like parabolic, right? It's not just a linear diagonal line. We have some sort of curvature. So that's telling us that we have a change in the rate at which our car is moving. So is this rate increasing or is it decreasing? Well, let's look at it, right? If the y-axis is the position that the car is moving, and the x is time, we see that it is slowly, it's covering less distance with time, essentially. So our slope is decreasing with time, so that means our velocity is going to be decreasing with time. Okay, so our velocity is decreasing with time, and then we get to some point about at like this, right? I try to put like number 1 right here to signify it. At about this point, I know it's not perfect, but about this point, the graph like levels off, right? So what does that mean? That means that we're not changing, we don't have any more displacement from that point on. So our velocity is 0, right? Yeah, so again, we start with some velocity. So let's say we start up here, right? So we start right here, and then whatever that value may be, and then it is going to be constantly decreasing. We're going to assume that this is a constant line right here, this little line that I made. That's a constantly decreasing until it reaches number 1, or 1 second, right? And once we reach 1 second, what happens? Our car stops moving, right? We don't see any displacement after that 1 second. So we're going to have 0 velocity after that. Okay. Again, if you have questions, comment or below this video, and I'll get back to you on it. Okay. Okay, cool. So then what is the acceleration? Well, again, acceleration is the rate of change of velocity. So do we have a change in velocity? Yeah, we have a change in velocity. At least before 1 second, we have a change in velocity. So what does this mean? Is our rate of change positive or is it negative, right? Is the slope of our velocity graph positive or is it negative? Well, it's negative here. So that's going to tell me that I have a negative acceleration, right? So you could think of it as this car is like decelerating, right? It's the rate of change is slowing down. If the rate of change is slowing down, then we have a car that is decelerating. If the rate of change is speeding up, then we have a car that is accelerating. Okay, so our car is decelerating, so we're having negative acceleration. So we're gonna have some negative acceleration. I didn't put values down, but we'll say we have some negative acceleration until we get to, right, first second. And then it levels off and we don't have any more rate of change. So we have 0 acceleration from that point on. Yeah, 0. From that point on. Okay. All right, so then for C, what do we got? So it's sort of similar to B, right? So we're assuming that our car is moving and it's moving at a decreasing rate. So it's slowing down essentially until we get to some point right here, which is like 1 second, we'll say. And then we see that our car stops moving and actually goes in the reverse direction. Okay. And it's just assume that this is sort of uniform throughout this curve. Okay, so how do we draw our velocity graph? Okay, so let's look at it. So let's say 1 second, right here. Okay. So again, just like we did in part B, right? It is the car is going away from origin in the positive direction at a decreasing rate. So that means that our velocity is decreasing at a is decreasing at a constant rate. So that's depicted by this, right? We're just going to draw that first half until 1 second, and then at 1 second we see that our car is going back to origin, right? So so essentially it's going back to origin, right? In reverse, it's going around, and so the velocity is now increasing, but it's increasing in the negative direction. Okay, so again, it's increasing in the negative direction because we we determine that this is the y-axis, and going this way in the y-axis is positive, going that way in the y-axis is negative, right? So in the first half, from this point on, we are going in the positive direction, right? We're tracing up here, the positive direction, and then from this point on, we're chasing and going in the negative direction, okay? So velocity, the first part is positive until we get to 1 second, and then our car reverses, right? And this also makes sense because at 1 second, our car stops, right? So we have a velocity of 0, okay? And it reverses, and all of a sudden we have a negative velocity, just like that, okay? So, and yeah, so like I said, our velocity is increasing, but it's increasing in a negative direction. So you can think of it as like our speed our speed here is increasing, right? So from this point to this point, our speed is decreasing to 0, and then from this point to this point, our speed is increasing, right? And again, note the difference between speed and velocity. Speed it does not have a vector. Velocity shows direction, which means it's a vector. Okay, so then acceleration, right? Acceleration. So our acceleration here, we see, or we know that the acceleration again is the rate of change of velocity. So whatever the slope of this line is for velocity is going to tell us where our acceleration is. Okay, so we see a constant decrease in velocity, or a constant negative slope in this velocity graph, right? So that's going to tell us we have a negative acceleration. Okay. So we have negative acceleration, and you know, whatever the slope of this line will be our acceleration. So I'm just going to draw a line down here. So if you drew a line that was below the x-axis, you can count that as right. Just because I didn't draw like any sort of units on here. I just wanted you to get sort of the general shape down. You don't have to calculate anything. But yeah, so that's essentially what we got for number 1. Again, if you have any questions, go ahead and ask in the comments. Okay, number 2. So 3 questions here. Which point on the graph has the greatest velocity? Okay, which point on the graph has a negative velocity, and which point is the object at rest? Okay, so A, what do we got? So which point on the graph has the greatest velocity? Okay, so what do we know about this graph? I didn't label axis here. Okay, so this is a position graph. I'll make sure I correct that. This is a position graph. So at which point in this graph has the greatest velocity? Well, we know again that the velocity is just the rate of change of position, right? So whichever point has the largest slope will have the greatest velocity, okay? So which point has the largest slope? Well, let's look at, I mean, A is pretty convincing, right? So I would say that A has the greatest velocity because the slope, right, the rate of change in X at that point is the highest. Okay, so that's why I would say A is the answer. Let me put colors. Let's say that A is a good answer for A. Whatever. And then B, which point has a negative velocity? Okay, which point has a negative velocity? Well, let's think about it, right? So again, we define the y-axis as going up is positive, going down is negative, right? So if we have, let's look at C, right? Let's look at C. So C, what do we think? Is that a positive or a negative? Would we have a positive or negative velocity at that point? Let's look at the direction or like the slope of what's going on, right? So let's start over. So from this point right here, right, our car starts moving, it speeds up, right, to A, and then we have at A, we determined before that's the greatest velocity, and then it slows down a bit, gets to B, and then it turns around, it starts going back to the origin, right? So if we know that velocity is a vector showing the direction, right? The positive and negative sign just shows the direction. Then we know that part C is the slope is negative, right? It's going back towards origin, right? So the velocity is going to be negative at that point. Okay. So B is C. Okay. And then for C, at which point is the object at rest? Okay. So I sort of gave away earlier. Our car is going, right? A has the maximum velocity, and then we slow down, and then we come to point B where the car stops and actually reverses in direction, starts going back to origin. Okay, so part B is the answer for that guy. Okay. All right, so part 3, or question 3. For each point, determine if the object is moving forward, backwards, or neither. Okay, so this is a velocity graph, so showing the velocity of each of the object. So again, remember that velocity is a vector, right? So it shows the direction, right? So the positive and negative sign on the velocity just shows what direction it's going. It doesn't really say much about like the magnitude or how like fast it's going. So let's look at look at A, point A. So is it moving forward, backward, or neither? So if we indicate the positive direction as going forward and the negative direction, right, a negative sign is going backwards, then this could be pretty simple, right? So A, it is above the x-axis. So pretty much anything above the x-axis is positive. We have a positive velocity at A, right? So that's going to tell me that my car is moving forward, right? Whatever, it doesn't matter if it's moving forward at a slower rate, moving forward at a faster rate. This question is just simply asking like if it's moving forward. So A is moving forward, so forward. Okay, B again is above the x-axis, so it has a positive velocity associated with it. So it's also moving forward. And then C is below the x-axis. So we have a negative, right? A negative velocity. This is going to be some negative value right there. The negative velocity associated with it. And again, velocity is a vector. Negative sign in this case is associated with moving backwards, right? So this is backwards. And you can think of this as like a car on the freeway, right? So let's say that the car is going with the grain, with the traffic, at some rate, right? It's moving forward, right? And then it turns around and then it starts going against traffic, and that's that's in the negative direction, right? Which is moving backwards in this case. Okay, so I would say that that car has a negative velocity in that sense. Yeah. All right, so number 4. Now we're getting into those equations, right? Those constant acceleration equations that we learned. So one piece of advice from here on out is to make your own equation sheet. It helps you with homework, helps you with studying, because the professor will probably post his equation sheet, maybe a couple of days before the test. But it's really helpful if you consolidate all those equations onto like one sheet of paper. I did that, and it helped me out so much, just like homework. That way I don't have to like flip through the lecture slides, try to find them and all that stuff. So it seems sort of tedious, but it'll help you out in the long run. So those 5 equations, right? So this guy, we got with an acceleration of that, how long, right? How long, there you go, there's a question right there. How long will it take a cyclist to bring a bicycle with an initial velocity of that to a complete stop? And then a second question, what is a biker's displacement? Okay, so how long will it take the cyclist to bring the bicycle with initial velocity, blah, blah. Let's do that one first. So the best thing to do with these problems is to write out your given. right? So what is the problem giving me? And then what does it want from me? So for the first part, so the first question, so let's say question A, what is the givens? Okay, so it gives us acceleration meters per second squared, initial velocity, so V naught, initial velocity, gives me a negative initial velocity, okay? Interesting, meters per second. And then it says it comes to a complete stop. So what does that mean? It comes to a complete stop, that means our final velocity is 0, right? And you can put, you know, in the book, or maybe another teacher would put VF, and then this would be like VI. So you can do it however you want, but I would probably stick to whatever the teacher is doing. So V naught is just the initial velocity, and then the V is the final velocity. Okay, so we got those two values. What else? That's about all that it gives us, right? Doesn't give us anything about position yet. So what does it want from us? Okay, it wants how long will it take. So it wants the time. Okay, so it wants the time. We have all those values, it wants the time. Okay, so now from this, let's look at what equation we can use to solve for time and find the time. Okay, so if we look at our, you know, equation sheet, we see that this equation right here looks pretty solid. So V equals V naught plus acceleration times time. Okay, that has all the variables that we have that are given, right? And it will give us time with that. We can't use any of the position equations because we're not giving anything for position, right? So that's essentially how you should try to work through these problems. It's like, what variables do I have, and then how can I plug these variables into an equation without having like two missing variables, you know, or two unknown variables. So this is easy, right? So we got final velocity is 0 equals initial velocity of negative 9.12. I'm just going to leave the units out just for simplicity, plus acceleration, 0 times the time. Okay. Okay, cool. So now when we solve, we got 9.12 equals 0.860 times time. And then time, we get 10, around like 10.6 seconds, right? Okay, 10.6 seconds. So you got to remember, or something to note here is we had a negative velocity. So what does that mean? We have a negative velocity. Well, again, you know, repeating myself, velocity is a vector. So all it's telling me is that our car is going in the negative direction, or sorry, our cyclist is going in the negative direction. Okay. And yeah, so our cyclist, if you remember from the first lecture, our cyclist is slowing down, right? So what do we remember about the signs of acceleration and velocity? What do they have to be? So the initial velocity is negative blah blah blah, and then the final velocity, or sorry, the acceleration is positive, right? So they're opposing signs, they're negative and positive. So that means that our cyclist is slowing down. Okay, you could have easily switched it and switched the direction of the cyclist and made the same thing, right? Or the same question. We would just have to have a negative acceleration at that point. That's just like bonus information. You don't have to worry about that. Okay, so for B, it wants us to know essentially the displacement. So displacement is just how far the biker went, the cyclist went. Okay, so we have all the same given variables. Now we have time. Perfect. So let's look at our equations and see what equation we can use to solve for time. So we have this equation right here, x minus x naught equals velocity initial times time plus 1/2 acceleration times time squared. Okay. You could also write this as delta x, and delta x is just an easy way of saying displacement, right? Because like we can, okay, so in this case, we're just gonna make the initial distance, so x naught is just gonna be 0, and then x is gonna be what we want, right? So I'll just do it that way just so it looks simple to you guys. So we want x naught will be 0, right? Or you could just ignore that and put delta x and that'll be your answer. And then the v initial, same thing, right? So we got negative 9.12. Oh, let's go on the next page. Okay, so negative 9.12, and the time is 10.6. All right, so plug and chug, basically 1/2 acceleration is what it was, and then time is the same thing, right? 10.6, that's a 10 squared. Okay, and then when you solve it out and you simplify and do all that stuff, x equals negative 48.4 meters. Okay, it makes sense too because our velocity is negative. Velocity is telling us which direction our cyclist is going. So our cyclist is going in a negative direction, so we're going to have a negative displacement in this case, right? Yeah, cool. All right, number 5. By the way, if I'm going too slow, I don't know if there's an option to speed this up. I think, yeah, it's actually going to be posted on YouTube. So you can like speed up videos on YouTube if you want to, or skip around. But yeah, do whatever you want. So an ambulance is currently traveling at 15 meters per second and is accelerating with a constant acceleration of 5 meters per second squared. The ambulance is attempting to pass a car which is moving at a constant velocity of 30 meters per second. Okay, how far must the ambulance travel? So how far? It's asking how far the ambulance must travel until it matches the velocity of the car. Okay, cool. So let's write out our givens. And if it helps you, you can draw a diagram, right? For me, the givens just sort of work the best. It's the most like time efficient. So let's look at what our given variables are. So let's look at the first one. So currently traveling at 15 meters per second. Okay, so our initial velocity, v naught, is 15 meters per second. It's accelerating the constant acceleration of 5 meters per second squared. Ambulance is attempting to pass a car which is moving at a constant velocity of 30 meters per second. How far must blah, 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 until it matches the car's velocity. So what is the final velocity going to be? Well, the final velocity is going to be, is going to match the other cars. So it's going to be 30. Velocity equals 30 meters per second. Okay. And then it wants us to know how far the car must travel. Okay, so how far does car travel? Delta x is what we want to know. Okay, and again, delta x is just x minus x initial, and x initial is 0. You can define it as 0 if you want. You can define it as whatever you want. Wait, 0 is the easiest. Okay, so cool. We got all our variables. What do we not have? Well, we don't have time, right? So that's not helpful. But it doesn't matter because we have all these other equations to help us out, right? So with doing system of equations, with those first 2 equations on our list, we can essentially eliminate the time variable. So we don't need time, and we can use this equation by doing that system of equations that he briefly mentioned in class to get this equation right here, so that we don't have to use time. Okay, so we can use that equation. There's no time variable in that. We have all those variables right there. And what do we want? Well, we want x. We want x, right? We want the displacement, or how far it went. So plug and chug, right? So 30 squared equals 15 squared. Yeah, plus 2 times 5 times x minus 0. Okay, and then when you solve it all out, you'll get x equals 67.5 meters. Okay, cool. So that's our answer, 67.5 meters. So that's how far the car traveled while it was speeding up to try to match the other car's velocity. Didn't catch up with it yet, but it matched the car's velocity, essentially. So that's that. Okay, so let's just go straight on to number 6. So number 6, an aircraft has a landing speed of 72 meters per second, and upon landing, it is able to come to a stop in 2,000 meters. Space. Oh, I like verbally dictated this, so some things kind of aren't mentioned. Assuming, sorry, I'm gonna exit that. Assuming constant, yeah, okay, constant deceleration. Yeah, I didn't change it. Assuming constant deceleration, how long would it take for the aircraft to come to a full stop? So assuming constant, yeah. So I verbally dictated this. I didn't check it. It's like 11 o'clock right now. Assuming constant, you can fast forward to this. Deceleration. How long will it take to do that, right? Just to kind of complete full stop. Okay, so given. What are our givens? So aircraft has a landing speed of 72. So our initial velocity, cool, 72 meters per second. Upon landing, is able to come to a stop in 200 meters. Cool. So 200 meters. Let's say delta x equals, sorry, 2,000 meters. 2,000 meters. And then what else do we know? Well, it's coming to stop. So we know our final velocity is 0 meters per second. Okay, and no other givens here. What do we need? Okay, we need to know how long. So we need to know the time. What is the time variable? Okay, cool. So do we have an equation to solve for this? Yes, we have an equation to solve for this. What are we missing? Acceleration. We're assuming constant acceleration or deceleration in this case. Just slowing down in the positive direction. So assuming constant deceleration, so that means we can use our equations, right? But we don't have the acceleration, so we're going to use this equation right here. So x minus x initial equals 1/2 times v naught plus v time, right? And then just plug and check. So, right, delta x equals x minus x naught. So I'm just going to say 2,000 meters equals 1/2 times initial velocity, which is 72, plus final velocity, which is 0, times time, which we don't know, right? And then when we solve this all out, we get a time of 56, around 56 seconds. Okay, so it takes 56 seconds for this aircraft to come to a complete stop, is what is going on there.
All right, let's power through these last ones. So 6, 7, and 8. So 6, what we got? So an aircraft is landing. Aircraft has a landing speed of 72 meters per second, and upon landing, it is able to come to stop in 2,000 meters. Assuming constant deceleration, how long would it take for the aircraft to come to a full stop? Okay, so givens, right? What are our givens? So landing speed is 72. Okay, so our initial velocity is 72 meters per second. Okay, and it's able to come to stop in 2,000 meters. Okay, so we'll say our displacement is 2,000 meters. Okay, so you could say like XO, like the initial X is 0 and the final X is 2,000. Okay, so final velocity, what is it? It's 0. Why? Because we're coming to a stop. Okay, and then the question is how long? Okay, so what do we want? We want the time. Time. We don't know acceleration or deceleration case. So what equation we're going to use? We're going to use this guy right here. We're going to use it's x minus x initial equals 1/2 v naught plus v times the time. Okay, and then plug all your values in, right? Why do we use this equation? Because it doesn't have acceleration in it, right? All the other ones have acceleration. You need acceleration to solve the equation. So we use this one because specifically we solved, we used those first two equations that are in our equation list. We did system of equations with them, and we found this equation. Okay, so then when we do plug and chug, 2,000 minus 0 equals 1/2 times initial velocity of 72 plus final velocity, which is 0, and the time. So when we solve for everything, time equals 56 seconds. 56 seconds. Okay, so it takes us 56 seconds to come to a full stop. Okay, so number 7. Let's go on to number 7. Ball is dropped off a cliff that is 1,000 meters high. What is the speed of the ball 1 second after it drops? What is the velocity 2 seconds after it drops? Okay, so A. Let's start with A. So what is the speed of the ball, right? What is the speed of the ball? Speed is vectorless. It's just a quantity, right? So we're not going to have a positive or negative sign in our answer. So what is the speed of the ball 1 second after it drops? Okay. So what do we know? Given, what was given to us? It's dropped off a cliff that is 1,000 meters high. So let's say that x initial equals 1,000 meters. X final equals 0. Okay. And then what else do we know? Let's see. Well, we know the time is 1 second. Okay, what else do we know? Well, there's something that's not explicitly stated in here, right? We're getting into the free fall questions, right? So in free fall, you got to assume the acceleration is due to gravity, right? So acceleration is negative 9.8 meters per second squared, okay? Yes, okay, so is there anything else? Yes, we know the initial velocity, right? What is the initial velocity? It's 0 meters per second. All right, so what do we want? We want the speed. So we can find the speed by using the final velocity, right? So what is the final velocity after 1 second? Okay, so real simple equation we can use here. We just use this guy. So v equals v naught plus acceleration times time. Okay, and when we plug in our numbers, so v equals v naught is 0 plus acceleration is negative 9.8 times the time, which you don't know time, or sorry, we do know time. times 1 second. Okay, so then the velocity is negative 9.8 meters per second. Okay, so it's negative 9.8 meters per second. So it's negative because it is falling towards the Earth, right? So does this make sense? Yes, it makes sense. Why does it make sense? Because our acceleration, what is our acceleration? Our acceleration is the rate of change in velocity, right? So if our velocity starts off as 0 and our rate of change in the velocity is negative 9.8 meters per second squared, then what will it be after 1 second? It'll be negative 9.8 meters per second, right? Because if that was what the rate of change in our velocity is, we would expect that to be the answer. Okay. And it's asking what the speed is. So what is the speed? Well, the speed is just 9.8 meters per second. Okay, because it's vectorless, just the quantity. Okay, it's the magnitude of velocity. Okay, and B. So what's B? B is similar, right? We have all the same givens. The only thing is our time is 2 seconds. So let's plug it in. So what is the final velocity? Initial velocity 0. Same acceleration. And then it's just 2 seconds. So our velocity is going to be, what is it, 19.6, I think. Yeah, 19.6 meters per second. Okay, does this make sense? Yes, it makes sense. Why? Because our rate of change in velocity is still negative 9.8 meters per second. After 1 second, it was negative 9.8 meters per second. After 2 seconds, it'll just be doubled, right? So 2 times negative 9.8. After 3 seconds, it'll be tripled, right? So it just keeps going on and on, just like that. Yep, cool. Okay, last one, 8. Let's pound it out. So 8, a ball is thrown straight up at 30 meters per second. How far will the ball travel when it slows down to half the original speed? All right, so let's write out the givens. Okay, so what are our givens? Well, ball is thrown straight up at 30 meters per second. That's a given. So our velocity initial equals 30 meters per second. Okay, how far? So there's a question. How far is the ball? So what's the displacement? Question mark. Will the ball travel when it slows down to half the original speed? Okay, so what does that mean? That means that the final velocity is half the original speed, 15 meters per second. It's half of the original speed. Okay, and then what's the given that's not given, right? What's the assumed given? Acceleration. Acceleration is negative 9.8 meters per second squared. Okay. We have enough to solve. The only thing we don't have is time, and that's okay, right? Because we have an equation that we can use that we don't need time. What is that equation? That's this equation. V squared equals V naught squared plus 2 times acceleration delta x. Cool, then plug and chug, 15 squared equals 30 squared plus 2 times negative 9.8 delta x. What is delta x? Well, that's what we want to find out, right? Delta x. When you solve it out, what do you get? You get delta x equals 34 point blah, 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 39 meters, right? Cool. So that's how far the ball travels when it gets to half speed, right? So a little diagram, a little person throwing a ball up in the air, right? So the initial velocity going up is 30 meters per second. Okay, and then let's say somewhere along this path, let's say right here, it reaches its 15 meters per second, which is half the original velocity. So we're trying to find the distance, the distance that is, right? So what is this? Well, it turns out to be 34 point blah, 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 right? Around 34 meters. That's the answer, right? And then up here, is where it stops. So it's 0 meters per second. Okay. So yeah, that's about that. So yeah, again, if you guys have any questions about anything that I did, go ahead and comment on the video and I'll get back to you as soon as I can. If you have any suggestions on sort of like what I can do differently, maybe I like ramble on too much about certain things, I can try to be more concise. You know, this is probably turning out to be like a 30, 40-minute video. But you guys, if you want to, you can totally just like scrub through the video, or like go at 2 times speed if I'm going too slow for you. It's up to you. You know, do what you want. Won't hurt my feelings. Yeah, if you guys know any cool websites to make worksheets, that would be helpful. If you know any websites to help me with these graphs, making graphs, that would help a lot too. Okay, cool. Yeah, thanks for watching the video. Trying to turn it off now.